Today we're going to implement linear regression from scratch in Python, specifically the closed form solution. I already have a video on this channel where I show you how to implement linear regression from scratch with all the mathematics and with the Python code, but using gradient descent. Today we're going to do the same thing with a closed form solution, which is the arithmetic algebraic solution, no gradient descent, no iteration, but actually just calculating the optimal parameters. This video is going to be quite mathematical. If you like it, let me know by hitting a like button and subscribing, but now let us get right into it. Alright, so this video is going to be split up into two sections. It's your decision if you want to watch both of them or just the second one. In the first one, we're going to cover the theory, the mathematics behind linear regression, specifically the closed form solution, the one where we calculate the optimal parameters. We don't iteratively get closer, we just calculate it with a formula. That is the algebraic solution, you could say. And it is going to require a decent level of mathematical understanding. You should know what partial derivatives are. You should know what it means when a derivative is equal to 0. You should understand matrix notation to some degree. Of course, you can also watch the first part just for entertainment or for seeing what it looks like, but I'm not going to explain fundamental math concepts. I am going to explain regression from scratch, so I'm not going to assume that you know anything about linear regression already, but I'm not going to go into the details of how to multiply matrices and what the transpose of a matrix is. So I assume you already know that. You can also, of course, skip the first section and just go to the implementation right away. And of course, as I mentioned in the introduction, I also have a second video on this channel where I do the same linear regression from scratch tutorial, but with gradient descent, which is a different approach. So let us get started now with the most basic question: what is linear regression? And for this, I'm going to use a very simple example, a two-dimensional coordinate system where we have an x-axis and a y-axis. And let's assume we have some data points. Let's say the x-axis is time spent learning, and the y-axis is score on exam. This is one idea here. So we have one variable which is free and one which is dependent. So we have the information: a student can study a certain amount of time, learn a certain amount of time. Maybe I should say studying, that's the proper word. Time spent studying. And then, of course, we have a score on the exam. Now, this is not a formula. Some people can study a lot and get a bad grade. Some people can study a lot and get a good grade. Some people can study very little and get a good grade. And some people can study very little and get a bad grade. But of course, if you have enough data points, you're going to see some pattern. You're going to see that for the most part, the points show a trend, which is the more you study, the better your score on the exam. Of course, you always have some odd outliers, but for the most part, the points are going to look something like this. For example, the question now is, if I was to plot a trend line, like a linear function, just a line without any curves, without any irregularities, what would be the best line to describe the trend I see here in the data? For example, one line I could draw is this here. But this line doesn't very much describe what's happening here. So we can see that the trend of the data is actually more diagonal from the bottom left to the top right. But this line, doesn't fit the data quite well. Neither does this one. This one here is better. This one here is also maybe good. The perfect line, I would say, is probably something like this. It's not the exact line, but something like this probably describes the data best. Maybe you have to adjust it a little bit, but something like this would describe the data best. This is now me just looking at the data and feeling it and saying that this line is good or perfect. But of course, there's a mathematical way to find the perfect line. And the reason you want to find the perfect line is because you can also make predictions. Once I have the perfect line to describe this trend, I can get some input data x here, the amount of time someone studied, and I can just look at my line and predict that the most likely score this person will have is this here. That is the expected value when I know that the person has studied this many hours, for example. Now, of course, this can also be extended to multiple dimensions. So I can actually go ahead and say that I don't just have x as input, I also have, for example, something else like hours slept before the exam day. So here I would have y, here I could have something like x2 and x1, and then I would say that I have some data points here. I know that this person has studied a lot, slept very little, and then I have like the y dimension here, how did they perform on the test. So that is all we can visualize, 2 or 3 dimensions, but of course you can have 1,000 different types of data points, 1,000 different dimensions, so to say. the only thing is with linear regression, you always need some linear prediction mechanism. So here you have a line in this space here. It would be a hyperplane. It's a bit difficult, like a plane. It would be a bit difficult to draw here. But if I have like the perfect separator, it would be something like this, where I have a plane cutting the three-dimensional space in half, and then in higher dimensions it's difficult to visualize, but it would be a so-called hyperplane, a linear structure in higher dimensions. Now, that is the idea. We are trying to find this perfect line here. But of course, this has to be done mathematically, not just by looking at it, especially if you have multiple dimensions. And also we need to define what does it mean for a line to be perfect. Now you can define that however you want, but the common way to define this is to say we want to minimize the distances between the line and all the existing data points. So I have these data points here, and every data point is not exactly, or most data points are not exactly on the line. And what I can do now is I can just draw lines, straight lines from the points to my prediction line, to my trend line here, to my regression line, and just calculate what the distance is. And this is my loss function, so to say. So this tells me how wrong my line actually is by incorporating all these distances here and summing them up. The problem with this is, of course, if I just sum them up, they can cancel out. What do I mean by that? If I have, for example, a coordinate system with just two values, let's say something like this and this. Of course, in this case, it doesn't make sense because the perfect line would then be this. But let's say that I still have this line to evaluate the error. And let's say the distance here is 2 and the distance here is also 2. Mathematically speaking, if I have to express this as a formula, I would have something like, if that is 10 and this is 8 and that is 6, then I would say 10 minus 8 is 2, but then I wouldn't do 8 minus 6 because I just do 6 minus 8, and that would be negative 2. And if I just sum them up, what would happen is I would get a loss of 0, even though I have some loss. So long story short, a simple way to counteract this is to just square the numbers, because if you square something like negative 2, if you take this to the power of 2, that is going to be a positive number, in this case 4. So what we're trying to do is actually we're trying to reduce the sum of squares. This is called the RSS, the residual sum of squares. So that is what we're trying to minimize. In gradient descent, what we did is we defined a loss function, and then we tried to just move down the slope. So if the loss function looks something like this, and you start somewhere here with random parameters, what we do is we just go down to the valley by going into the direction of steepest descent. That is the gradient descent approach. What we're going to do today is we're going to do an arithmetic solution just by looking at the formula and determining what we're trying to do. And then we're just going to get something where we can plug in the input values, where we can plug in the parameters, and we're just going to get, or the input values, the output values, and we're going to get the optimal parameters as a result. For this, of course, it makes sense to first understand what a line looks like when you write it down in mathematics. A line has the structure y is equal to mx plus b. This here is the slope, the m is the slope, and b is the intercept. That is the basic structure of a line in mathematics. So if I have a basic coordinate system again, and I say here we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then also on the y-axis 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, then I can say any line can be plotted in some way. Any line can be described in some way. If I have, for example, a line that goes through these points, like this, for example. Actually, this is not a line because the coordinate system is not drawn perfectly, but theoretically it would be a line like this. That line has an intercept of 1. As you can see, it doesn't go through the origin, so it has plus 1. That is the b value. And the slope is basically how much does it increase with each step, which is also 1. So in this case, that would be just x plus 1. And you can do that with different lines. So something like this, for example. Every line can be described in terms of a slope and an intercept. That is the basic idea. So with our residual sum of squares, how can we define it? We can say that the error is essentially just iterating over all the examples that we have, so I equals 1, up until n data samples that we have. And what I want to do is I want to just see, okay, what is the actual output? What is the correct value for the score on the test, for example? And what was the predicted value by the line? So where is the line at this point? And that would be y hat, for example. And that is always for the sample I. So I'm just taking that and squaring that to make it positive. This would be the residual sum of squares. Now, we can also expand this and say that actually what we have here is just yi, minus, and then we have our parameters. We have the input, so that is just m times x plus b. So whatever my slope is, times x, and then plus b. That is actually my prediction here. And that's equivalent. This is what that actually means. That is yi hat. Now, of course, we have multiple dimensions, so we can actually write this down as a vector. M cannot just be m. I could also have something like in multiple dimensions. I could have y is equal to m1 times x1 plus m2 times x2 and so on, plus b in the end. So that is also possible. So I should actually use vector notation, matrix notation. But fast forward, what we can do if we write this for multiple examples, because I can of course also calculate this not as a sum, but as a matrix calculation. What I have is I have essentially all my coefficients and I have my input. And we can also make a trick here. We can do a trick in order to not have to write b separately. We can just say we have x1, x2, x3, but we can also say x0 is just always going to be 1 and m0 is just going to be b. So then basically we have one vector here, which contains 1, x1, x2, x3, and so on. And then we have another vector which contains b, the intercept, and then m1, m2, all the slopes for their respective dimensions. And once we have this, we can write this down in a more fancy notation, because then we can say, instead of calling this m and b, we can just call this beta. This is my coefficients or my parameters, we could also say here, are just called beta. And then here I have my input x. And now, of course, if I don't just have one x, but I have multiple x because I have multiple data samples, I'm not just looking at one specific input, but I'm looking at 1,000 data points, for example, then I can say x is just a matrix. X contains multiple samples, multiple dimensions, and beta also contains the coefficients. Beta is just the coefficient vector. We don't need different coefficients for different samples. We always have the same. We're just fitting a single line. But that is essentially how we can write this whole thing too. So on a smaller scale, we could say that yi or y hat I is basically just taking xi and multiplying it with the coefficients. Provided, of course, that we have the 1 here as well for the bias term or for the intercept term. But how I actually want to write this now is looking at RSS, which is just the squared sum of the differences. We can just do this in matrix notation. So I can say the RSS given the coefficients beta, so the error term that we have, the loss that we have given the current set of parameters, the current set of coefficients, is essentially just a matrix square. So it's basically just y, the actual true vector, the actual result vector with all the true outputs, minus taking all the inputs and multiplying here, doing the dot product here, with the coefficients that we have. And since we cannot just do squared now, we need to say transposed and then y minus x beta as well. This is just how you do it in matrix notation. Basically, it's just squaring the same thing. So you're taking the difference, squaring it. That's the matrix notation. So now we need to derive something where we can say, at the end of the day, I want to have the optimal sets, the optimal set of coefficients, beta hat, let's call it. This is the optimal set of coefficients, that this is equal to something that I can just calculate. And this something will probably include x and y in some way. So how do I derive this? I derive this by taking a look at this, expanding it, and doing some stuff to get it into a nice form. So first of all, I can just say, let's expand this. So I can say y and y, it's basically just y transposed y. Then minus, and I can say here, it's going to be this transpose, so it's going to be beta transposed x transposed y. And then we can say here y transposed x beta. It's not going to be the perfect notation, by the way. I'm sure I'm making some mistakes here. Also, I'm not a mathematician. I'm just a computer science guy. But I think I'll do decent here. And then for the last one, we can just square it as well. So we can say basically plus, because we have two negatives, so we have beta transposed x beta. That is just the binomial formula here with the matrix notation. And what we need to do now is we need to simplify this, or we can simplify this rather, because this essentially here and these are just scalars. So we can basically treat them as 2 times the same thing. So we can say y transposed y, and then 2, and then beta transposed x transposed y, plus beta transposed x beta. And with this now, we need to ask ourselves, how do we find the optimal solution when it comes to the coefficients? Well, what we can do is, this is the loss function. We want to minimize the loss function. So minimizing doesn't mean that the loss is going to be 0, because if I set the loss to 0, that's not guaranteed that this is even possible, because a line cannot fit any data, so we might end up with some loss in the end. But we want to minimize this loss. So we want to actually say there is no gradient, or the gradient is 0 at this point. So think about it this way. If I have a function like this, at this point here, the derivative of this function with respect to the input is going to be 0. Not the function itself is going to be 0, but the derivative is going to be 0. So what I actually want to do is I want to take the partial derivative of RSS, of the residual sum of squares, with respect to the parameters, because that's the thing that I'm tweaking. I'm tweaking the parameters to get the most, the smallest or the minimal loss, the smallest loss I can have. And this basically means I'm taking this and I'm taking the derivative with respect to beta. So in this case, there's nothing, so that's just going to be 0. Minus, here what do we have? We have x transposed y 2. So basically we can just say 2 times x transposed y. And this one here is maybe a bit tricky if you're not used to that. It's basically a square, so you can treat this, if you get out of the matrix world for a second, that's basically like x squared b squared. So you keep the x squared, but you have to say 2 times b. So yeah, in matrix notation, that would mean we drop one of the betas, but we add a 2 because the square has to be taken down. So you have 2 times xtx beta. And that is now much easier to work with, because now I have this statement. I can easily say now, since this is 0 minus and then plus, I can just take this here to the left side, and I can say that this essentially means 2 times x transposed y is equal to 2xtx beta. So what I can also do now is I can get rid of the 2, and what I want to have, I should say, if I set this to 0, and of course, sorry, I missed this point actually. This is an important point. I need to mark this red because I missed this. We don't just take the derivative, we set it to 0. I actually said that, but I didn't write it down. So this thing here is set to 0. This is why we can actually take this to the left side, or the right side in this case now. This is why we bring this over to the other side, because there's a 0 there. We're trying to set this equal to 0. And what we get as a result is beta hat, the optimal set of parameters. Now, how do I get beta hat here? I need to get rid of this here. We're just going to assume now that this is going to have full rank, that this is invertible, so to say. And essentially, we're going to divide by xtx, or x squared, whatever you want to call it. And we're going to do that by multiplying with the inverse. So by multiplying with x transposed x inverse. So that is going to be removed here. And on the other side, we're going to add it. So at the end, we're going to get beta hat is equal to, and now x transposed x, the inverse of that, times x transposed y. That is the closed form solution to linear regression. So now let us put all of this into Python code. That's going to be quite simple and straightforward. We're going to do it from scratch, but we're going to use NumPy, which is an external Python package. So if you don't have it on your system, you have to say pip or pip3 install NumPy. And if you want to use a virtual environment, you can create one. In my case, I'm just going to use UV for that. And I'm going to say UV add NumPy. Don't worry about this. You can just do pip install NumPy if you don't know what UV is. No need to use it. So open up a main py file, and here now we're going to write the code for our linear regression using the closed form solution that we just saw, that we just derived. So for this, I'm going to say import numpy as np, and I'm going to create a class called linear regression closed. And that is going to be structured in a similar way to the classes in scikit-learn. So I'm going to have an init method. I'm going to say def init with self. For now, I'm going to pass. Then we're going to have a fit method taking self, x, and y. and then I'm going to have a predict method. So predict self x, and that's basically it. So what do we need to do? First of all, we need to make some space here. We need to define what we are going to train. So we're going to have the coefficients. I'm going to say coef underscore. The reason I'm saying underscore is because that's a convention. I think that it's introduced by scikit-learn actually. This convention that when you train something, when a parameter, a variable, an attribute is learned, then you just add an underscore in the end to signal that. So self coefficient is going to be none, and then self.intercept is gonna be 0.0. So these are basically the m's, this is the b, and the whole thing is going to be the beta in terms of calculations here. That is all we need to initialize. Now for the fitting, this is where we actually apply this final formula that we had. How do we do that? We first need to take the data and turn it into numpy arrays if the data is not already in the correct format. So I'm going to say here x is equal to np array of x, y is equal to np array of y. And now what we need to do in order to also add the intercept and train the intercept is we need to add this 1 to the x vector. So I'm going to say xb is equal to np concatenate, so npc. And we're going to say np once the shape of the data. So it's going to be x, actually, x dot shape 0 and 1, like this. That's going to be the ones. And we're going to prepend this to x. So the basic idea here is I have a bunch of values, x1, x2, x3. And before that, I just add a 1 so that I can multiply this with the intercept, with the bias, so to say. And then I do the calculation that we just discussed for the entire matrix. So I'm going to call this A now. And now we just basically need to put into code the formula that we just had. So that is going to be NP. We had the inverse of X transposed X. So NP linear algebra. So NP linalg inf. And that is going to be the inverse now of X transposed multiplied with X. So that here is the dot product operator in NumPy. This basically means x transposed x, take the inverse of that. And of course, you don't want to do that with x, but with xb, where we have the 1 in there as well. And then the whole thing times xb dot t, and then dot product y. That is exactly what we had. The only difference here is xb because we have this 1 prepended here. But that's exactly the formula that we just derived. We had the inverse of x squared essentially, then times x transposed, and then times y. That is the formula, that is the closed form solution. And now we can just say that our coefficients, or let's start with the intercept. The intercept is going to be the first element of the resulting matrix, so the first row, so to say, and that is going to just be 0, and the coefficients are going to be the rest of this matrix. This is basically all you need to do the training. Now, in order to apply it, you just need to take the trained coefficients and the intercept, and you need to apply it to x. So we just have to say here x is equal to np array of x, and then we're going to return x dot product with the coefficients plus the intercept. There you go. That is linear regression from scratch in Python. Now let's give it actually a try and see if it performs well. How do we do that? For this, I'm actually going to use scikit-learn, not for the model itself. It's already implemented. I'm going to use scikit-learn to load a dataset and evaluate it, and also to compare it with the scikit-learn implementation of linear regression. So I'm going to say uv add scikit-learn. In your case, you can say pip or pip3 install scikit-learn if you're not using uv. And then what I'm going to do is I'm going to say at the very top, from sklearn.datasets import fetch California housing. From sklearn.metrics, I'm going to import the R2 score or R squared score. And then from sklearn.linear models, I'm going to import linear regression. And now we can just initialize our model. We can say rec is equal to linear regression closed. Then I can say x and y is equal to fetch California housing, return x, y equals true. And then I'm going to say rec fit x, y. And then I can also say the predictions. I'm going to just evaluate on the training data just to see if the algorithm works. So y prediction is rec predict onto x. And then I'm going to print the R2 score of y and y prediction. So UV run main py. It's not linear models, it's linear model. So let's see. And I get this R2 score of 0.6. Now, to see if that's a good score, if that's the correct score, so to say, we can do the exact same thing now with linear regression from scikit-learn. So I can say rec sk is equal to linear regression. And I can try the same thing. I can say rec sk fit xy. And then, yeah, basically I can just copy this part here, paste it down here, and replace rec with rec sk, and then I can just run this again, and we can see we get the exact same score, meaning these are basically equivalent. So you can see this works. You can also see it works from multiple parameters. We can take a look at the data actually when we load it. If we take a look at x, you're going to see that this is actually not just one value. We have multiple values per instance. So this is already a very good implementation because we're using the matrix notation, because we can work with multiple dimensions, we can work with multiple features and everything. And yeah, that's basically linear regression from scratch. The magic here is what happens in this line. This is what we derived in MyPaint before. This is just prepending a one for the intercept term. You don't even need to do that necessarily. If you don't want to use the intercept, if you don't want to fit the intercept. But that is the basic idea. This is how you can do linear regression from scratch in Python with the closed form solution. So that's it for this video today. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, in case you're interested in that, I do offer one-on-one tutoring and also services. You can find both of these on my website. I have 2 tabs, tutoring and services. There you can see what I have to offer, either for teaching you something or for doing something for you in terms of services. You can contact me via LinkedIn or email on both pages down below. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.